Hello everyone. I hope I am audible. So today we'll conduct the tutorial, eighth tutorial of this tutorial series of the course Measure and Integration. So this is NPTEL course, and the course code is hopefully NOC 25 MA 68, and today is 13th September. Okay. So in today's this tutorial, we will be discussing problems which will be helpful to solve the assignment 8 of this course, of this NPTEL course. So, so today's most of the problems will be based on the bounded variations, functions of bounded variations, and relations with the integrations, with the measurable integral functions. Okay, so let's start with the problem, and whenever we required, we will be uh, stating the some of the what is called definitions or the theorems, whatever is required. Okay, so let's give a problem. Let f from AB to R be a monotonic function for x belongs to open interval AB. Define fx plus is equals to limit h tends to 0. This means h is decreasing to 0. This particular thing means this h is decreasing to 0. So that means h has to be positive. Limit h tends to 0, f of x plus h, and f of x minus is equals to limit h decreasing to 0, f of x minus h. Okay, so this is the defined. Question is, this is how it is defined, fx plus and fx minus at a point x belongs to open interval AB. Question is, so that f x plus and f x minus always exist. Deduce that the set of discontinuities not continuities, set of discontinuities of f is at most countable. This is what is the first problem. Okay, so let's try to solve this problem. Okay, okay, so we'll be solving this one. Just let me keep on this. Okay, so Yeah. So you have to show that these two exist finitely. So that we have to show. Okay. So always exist. Okay. So that means we have to show that limit h tends to 0 f of x plus h is now note that. So how we will show that? One thing, f is monotone function. So let f is monotonic increasing. That is for any x and y belongs to open interval AB with not open interval, actually closed interval with x less than equals to y, x less than y, then fx is less than equals to f of y. This is means the monotonic function. So we have monotonic increasing function. So let's take f is a monotonic increasing function. Let x is a point in between OB of interval. Then note that for any x and y, for any y belongs to open interval AB or actually closed interval A to x, f of y is less than is equals to f of x. Okay. So let's take supremum of f, that is f is bounded. Okay. That is f is bounded on ax. In fact, f is bounded on the full interval AB. It is bounded by the value fb. Okay, but for now, f is bounded on f of a on interval ax. Let so there exists supremum. If it is bounded on this interval, then let's take supremum of supremum y belongs to ax of f of y, that is, suppose this is equals to n, and that must be less than equals to f of x. Okay, because if for every y belongs to closed interval ax, f of y is less than equals to f of x. So therefore supremum, whatever the supremum will exist, that will be less than equals to n. And then by definition, and we will show that we will show that limit h decreasing to 0 f of x plus h, f of x plus h, this is equals to n. Okay. Okay, 1 minute. So okay, so then I have to take in reverse way actually. Okay, so basically we will show that other one, limit x minus h is equals to n for h tends to 0. That is what we will show. Okay. Yeah, this is what we will show. So what we get here actually, by the definition of supremum, by the definition of supremum, by the definition of supremum, for for given any epsilon greater than 0, there is a point x naught belongs to the interval ax such that u minus epsilon, that is less than epsilon naught, this is m minus epsilon, this is less than equals to m, and that is less than equals to m plus epsilon. That says that for any given epsilon greater than 0, if we consider delta is equals to let delta is equals to x minus x naught, then for the given epsilon greater than 0, for the given epsilon greater than 0, there exists an delta greater than 0 such that whenever h is less than delta, mod of h, this is positive, mod of h is less than delta h, such that whenever h is greater than 0 and h is less than delta, then x minus h, that must be less than um, then x minus h, that must be less than x, and that will be greater than x naught, basically x naught, which is equals to x minus delta. Basically, if h is less than delta, x, and suppose this is the point x naught, this is the point x, so this is the distance delta. If we consider h here, in between, if we consider h is distance from this to this, some points, then x minus, okay, then x minus h will be greater than is equals to, then x minus h will be greater than is equals to uh, x naught, I guess, minus h minus delta. Okay, so minus delta less than h minus h. So x minus delta less than x minus h. So x minus delta is equals to x naught. Okay. So this is less than equals to x naught. Okay. This is less than, not less than equals to. This is strictly less than x naught and less than x. Okay. Then and so f of x minus h, that will be less than m minus epsilon, less than m plus epsilon. Okay, this is positive, and this is true for every age. This is true for every age greater than 0 such that h is less than delta. That that limit h tends to 0, f of x minus h, that must be equals to this m, because this is giving that mod of f of x minus h minus m less than epsilon whenever h is tending to 0. This is what it is giving, or basically whenever h is less than delta and h is positive. Basically, this is the thing. So uh, that says that this is the supremum. Okay, this is m has to be the supremum. This is what it is mean. Okay, so that means the limit exists. So therefore the limit exists. Therefore the limit exists. Similarly, by taking m is equals to infimum of f of x, where f of y, where y is coming from the interval x to b. One gets that, one gets by the definition of infimum. Okay, why this happens? F of x minus h. Why this happens? Because by monotonicity. Here is the monotonicity using. They are using monotone increasing, because if x not less than equals to x not less than x minus h, then f of x naught has to be less than equals to f of x minus h. Okay, so now f of x minus h. Okay, one can uh, I'll give a little argument. So so here I'll give a little argument why this thing are happening here, because due to the monotonicity, how monotonicity is working, so one gets the every h greater than 0 such that h is less than delta. Uh, how the monotonicity says gives this. Note that note that if x not less than x minus h, monotonicity gives that f of x naught less than f of x minus, this is less than equals to, but f of x naught is less than greater than epsilon minus m minus epsilon, and f of x naught h, this is less than is equals to f of x because of the monotonicity, right? Because x minus h is less than x, but uh, no, this is less than epsilon because x minus h is in the interval. This is less than epsilon. This is less than equals to m. This is less than m plus epsilon. So here is using the fact that m is the supremum of f over the interval a to x. So x minus h is as x minus h is inside that interval. So we are having this particular thing. Okay. So this is similarly by taking m equals to this, one gets by definition of infimum and the monotone increasingness, and using monotone increasingness, using the monotone increasingness, monotone increasing property, one gets that limit x tends to 0 f of x plus h, limit h tends to 0 f of, actually h tending to 0 means h is decreasing to 0, f of x plus h is equals to m exists finitely. Okay, this completes. So therefore f of x plus h, therefore, and similar argument for the monotone in decreasing functions one can do. Monotone decreasing functions solves individual functions, solves the first part of the problem, solves the problem. Okay. Now what we need, the second part of the problem says that this is the first part, so that fx plus fx minus always exists. Second part, that deduce that the set of all discontinuities of f at most countable. Okay, so here we will see how the set of all discontinuity is at most countable, why there can't be more than countable discontinuity. Okay, so recall that. Now we'll settle the problem. The set of discontinuities countable. Okay, is at most countable, is at most countable. Okay, here we will show this. See this. Let's take, let x naught belongs to the interval a to b, is a point of discontinuity of a, point of discontinuity of a, that is limit h tends to 0 f of x plus h. This is not equals to f of limit, this is x minus x minus x minus limit x tends to 0 f of x plus h, which is equals to f of x plus. Note that first of all, that f function, note that f is continuous at x naught if f of x naught plus is equals to x naught minus. Here is x naught, here is x naught, here is x naught, here is x naught. So here it says, as the function is not continuous, so that is says that the function is not continuous. That means we have this particular thing. Okay. So, but also when f is monotone increasing, then f of x naught minus h is less than equals to x naught plus h for all h greater than 0. This has to be, as x naught minus h less than equals to x naught plus h, not less than, this is strictly less than. Okay, this is, so therefore, but here it is claiming that this is not equal, but equality can't happen. So equality is not possible at x naught due to the discontinuity, that is limit x naught minus h tends to 0 is less than, strictly less than, h tends to 0 Okay. Okay, so this is it. So let's take x r1. Let r naught be a rational number. R naught belongs to this value, limit h tends to 0, x naught minus h, limit h tends to 0, f of rational function, rational value. Now, also note that for any other point, note that if x naught dashed be a point inside the interval AB, then and x naught dashed is less than x naught, then limit h tends to 0, f of x naught is um, that is less than is equals to limit h tends to 0, f of x naught minus h. Okay, x naught dashed minus h. Sorry, this is dashed. Then if there is so then if r not dashed be the corresponding choice for x not dashed, then r not dashed is strictly less than r naught. That is, for every distinct discontinuities is on the interval AB, there there is a distinct rational number. For every distinct discontinuity, there is distinct rational number. So now, if number of discontinuities of f is uncountable, this will essentially give uncountable number of distinct rational number. Uncountable number of distinct rational number, which is not possible. So, therefore, number of therefore the number of discontinuities of f is at most uncountable. Sorry, at most countable. This completes the solution of the problem. Okay. So this is the solution of the problem. So let's do another problem. Problem 2. For x belongs to -1 to 1, define f of x is equals to x sin 1 by x if x not equals to 0, 0 if x is equals to 0. Then compute, question is compute d plus f comma 0, d plus f, d sub f comma 0, d super minus f at 0, d sub minus f at 0. Okay, where is d plus f of x is equals to limit supremum f of x plus h minus f of x by h, d plus f of x is equals to limit infimum f of x plus h, f of x by h, and d minus f of x is equals to limit supremum f of x minus f of x minus h by h, and d sub minus f at x is equals to limit supremum f of x, sorry, limit infimum f of x minus h by h. Limit supremum h tends to 0, every time h tends to 0, h is positive, always h is positive, h is decreasing to 0, this is what is mean. Okay, d plus is equals to limit supremum f of x plus h minus f of x, f of, and d minus limit supremum h every time decreasing to 0, f of x minus f of x minus h by h, and d plus f of x is equals to limit infimum h down to 0, f of x plus h minus f of x by h, and d sub minus f at x equals to limit infimum h down to 0, f of x minus f. So this is the thing. Now the question is that find this one, compute this one. This is the question. Okay, so let's try to compute. This is very easy. Okay, so let's try. So note that f of h minus f of 0. So we have to take x is equals to 0. This is first. F of h minus f of 0. What is the, note that f of h is, here f is defined like that, x sin 1 by x if x not equals to 0, and 0 if x equals to 0, but as h is positive, so f of h is positive. Note that for h greater than 0, note that for h greater than 0, f of x minus f of h minus f of 0 by h. H is positive, so we have to use the previous first description of this description. So that is h sine 1 by h minus f of 0 is 0 by h, which is equals to sine 1 by h, and f of 0 minus f of minus h by h, which is equals to 0. Minus h is minus minus plus sine 1 by minus h. This is what it is, which is equals to minus of sine 1 by h. Okay. So now note that if h tends to 0, then sine note that if h tends to 0, then 1 by h tends to infinity, then sine 1 by h will oscillate frequently in between minus 1 to 1. Moreover, supremum moreover supremum of h greater than is equals to 0, not greater than equals to 0, supremum of h greater than 0, sine 1 by h, that will be plus 1, and infimum of h greater than 0, sine, so therefore minus h, that doesn't matter, therefore an infimum of sine 1 by h, that will be minus 1. Okay, this says that this says that d plus f at 0, that is equals to limit h turns to 0, limit supremum, whatever it is, sine 1 by h, this will be plus 1, d plus f0, that is equals to limit infimum, that will be minus 1, d plus f, sorry, d minus f0 is equals to limit supremum of minus sine 1 by h. So note that sine 1 by h has the supremum value 1 and infimum value minus 1. So minus sine 1 by h will have the supremum value 1. So therefore limit supremum is equals to 1, and d minus f at 0, which is equals to limit infimum h tends to 0 minus sine 1 by h, that is equals to minus 1. So the limit does not exist, but that is not our question. Our question is just to compute this one. Limit will the function will be differentiable at the point 0. So where one can say that Riemann, the f will be differentiable if and only if all the above all the above limits are equal. So the given function is not differentiable at x. So the given function is not differentiable at x equals to 0. Okay, so this is the another question. Now we'll go to the another question. So let's write that problem. Just a minute. Okay. So, so the next problem is that problem 3. So that so that the function a defined 0 1 by f of x is equals to x square sin 1 by x if x not equals to 0, 0 if x is equals to 0 is of bounded variation. This function is of bounded variation. So what is a bounded variation function? So let's recall little bit. Recall a function, a real valued function f from a to r is said to be of bounded, said to be of bounded variation if said to be a bounded variation if supremum of said to be a bounded variation if supremum of P belongs to capital P. What is capital P that I am saying, and TPA. What this is that I am also saying. What is this? Is finite, where P is the collection of all partitions P that is equals to x naught, which is equals to a less than x1 less than x2 all the way xn is equals to b. Okay, any partition. This is any partition. First point and second point, and t p is equals to summation of mod xi minus, this is for particularly for this p, n minus 1 I equals to 112. So this is what it is called. The if this is TPF is the summation of I equals to 1 to n mod of fxi minus mod of fxi minus 1. Okay, this is the mod, and P be the collection of all partition. This is the partition. I mean, so let's take P is a partition. That means there exist n nodes. This point x naught, x1, x2, xn. These are called nodes, and such that this supremum is called T. This maximum is called this summation is called TPA. Now, if I take collection of all partitions of every length of any length, and if we consider the TPA, then that will give some value that can be finite, that can be infinite, but here it will be finite because f is a real valued function and we are considering a fixed value. So this is finite for each fixed partition. It is finite, but the supremum need not be. Okay, so if the supremum is exist finitely, then we say the function is a bounded variation. Okay, now the question says that whether this function is a bounded variation or not. Okay, so here the function is a bounded variation. Why? So here we have to show that the function is a bounded variation. Why? So note that f dash x is equals to what was the function x square sin 1 by x square cos 1 by x sin 1 by x derivative and 1 by x derivative minus x square plus 2x sin 1 by x. Okay, if x not equals to 0, and if x equals to 0, then what is the derivative value? Derivative value is that, and f dash 0 is equals to limit h tends to 0 f of h minus f of 0 by h, which is equals to h square sin 1 by h, which is equals to limit h tends to 0, which is equals to limit h tends to 0 h sin 1 by h, that is equals to 0. Why this is equals to 0? Because sin 1 by h, this is always bounded by minus 1 less than equals to 1. So minus h less than is equals to h sin 1 by h, this is less than equals to h. Now taking limit h tends to 0 in each of these forms, so what will get? This is 0, this is 0. That means this limit has to be 0, and this is by sandwich theorem. You know the sandwich theorem of the limit, so this is the same way. So this is 0. So function is differentiable. So therefore f is differentiable. Whatever the interval it is given, okay, on 0 1. And f is differentiable on 0 1. Okay, and what is other thing one can say? It's bound. And mod of f dash x, this is less than is equals to, this is the point, so this will be like mod of cos 1 by x plus mod of 2x sin 1 by x, this is less than equals to 3 on this 0 1 interval, because on 0 1 interval 2x mod of 2x is less than equals to 2, and that will be less than equals to 3. Now for any 2 point x2 belongs to 0 1, f of x1 minus f of x2 by x1 minus x2 into distinct point. I can take distinct point. Distinct point is equals to f dash x1 plus theta h, or we can write f dash xi for some xi belongs to open interval x1 x2, let x1 less than x2. This is via mean value theorem. Okay, this is via mean value theorem. Therefore, this is via mean value theorem. Therefore, mod of f of x1 minus f of x2, that is equals to mod of f dash xi into mod of x1 minus x2. That is less than is equals to 3 mod of x1 x2, and this is for all x1 x2 belongs to 0 1. Then f is Lipschitz function. Okay, and whenever it is Lipschitz functions, then for any partition p is equals to 0 equals to x naught less than x1 less than x2 all the way xn is equals to 1, summation of I equals to 1 to n mod of fxi f of xi minus 1, this is less than is equals to 3I equals to 1 to n mod of xi minus 1, and this is equals to 3 into 1 minus 0, this is equals to 3. So therefore this is true for every partition. Okay, so that is for every partition p of the interval 0 1 ppf is less than equals to 3. Then supremum p belongs to supremum of p belongs to the all partition p of all partitions of 0 1. So one can write this is exist, that is f is of bounded variation. F is of bounded variation. F is a function of bounded variation. F is a function of bounded variation. Okay. Now this completes the proof of the solution of the problem. Now the another problem. Hmm. Okay, let me think just one. Okay, so let's do another problem. Just a minute. Let okay, that's supremum. Okay, so now problem number 4. What it says, let if from close interval AB to R be an absolutely continuous function so that TABF is equals to TAB is equals to integration AB, oh sorry, TABF equals to TACF plus TCBF. Okay, what is TACF and TCBF? That I'm so that acha, let it be a function of oh, let it be a function of bounded variation. Be a function of bounded variation. Function of bounded variation. Let A less than C less than equals to B, so that this okay. This is the question. So this is the question. Question is let A from AB to R be a function of so let here is the question is that let A from AB to R be a function of bounded variation. Let A less than equals to C less than equals to B, so that this holds TABF equals to TACF plus TCBF. And what is where TAXF is equals to supremum of this value. Actually, the um, considering f as a function, considering f as a function on a to x. So considering f as a function on a to x, considering f as a function on a to x, so if we consider this supremum, the whatever the supremum will exist because function is a bounded variation. Here the given function is a bounded variation, so therefore this supremum will exist finally due to the bounded value. This will exist finally as the function is a bounded variation. This will as f is of f is a function of bounded variation. So let's try this one. Okay, so we'll this is not tough. Okay, let's see. So now for any partition P, let let A less than C. Let note that if A is equals to C is equals to A or C equals to B, in that case the above equality holds. Why the above equality holds? In that case, in that case, if C is equals to A, T A A F is equals to 0 and T B B F is equals to 0, I think. Yep, B B equals to 0 respectively. So in that case it is done. So let C is a strict value, taking strict number, that strict value from A to B. Okay. If we consider this, let x naught let x naught is equals to A less than n less than x2, that in that way xn is equals to B, be a partition of be a partition of AB. Okay, take be a partition P of AB, take a refinement, then there is I naught belongs to this set, but there is I naught from 1 to n, 1 less than is equals to, yeah, 1 less than equals to I naught, that is less than equals to n, such that C will be lying between x I naught less than equals to C less than equals to x I naught plus 1. Okay, take a refinement, take a refinement of the partition P, refinement refinement P dash of the partition P, such that by by in by plugging C in between x and y. Thus, by plugging C in between x I naught plus 1, but plugging in between, plugging C as a node point in between. Okay, so basically what it is saying, the partition will be x1 x2 less than equals to x I naught. If 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 C is not there, if C is neither x I naught, I mean if C is equal to anyone, then any one of these nodes points, what are the nodes? That x1, x2, xn, these are the nodes. Okay, so if C is any one point, any one of them, then we don't need to do anything. If C is not any one of them, then we will be considering a refinement of that partition by considering just plugging this C naught point as an extra point. So this will be now like this way. This will be that this will be less than x I naught. This is less than C. This is less than x I naught plus 1, and all the way up. This will be the new partition. Okay, P dash. If if C is already a point of that partition, then we don't need to do anything. Okay, that will be the same thing. Okay, we'll be considering the same partition. If the PC is already a point of that partition. Okay, then then the new, with respect to this new partition p dash f, so p dash f will be is equals to supremum of I equals to 0 to, not I equals to 0, I equals to 1 to, I equals to 1 to I naught minus 1, I naught mod of, oh, this is not supreme, this is just summation I equals to 1 to the mod of xi minus xi plus 1, okay, mod plus mod of xi naught minus mod of fc plus mod of fc minus, just a minute, one second, there is a problem with my pencil. Just a minute, I have little issue. My pencil, yeah, I think not working. Okay, so mod of f of c minus f of x I naught plus 1 plus summation of I naught, summation of I equals to, or you can I equals to I naught plus 1 to n mod of xi minus xi minus 1. Okay, I hope I have written correctly. Oh, this is minus, so this will be this minus 1, so this will be up to my I naught, so I naught minus 1, so this will be like xc minus I naught, and this will be fc f of minus fc. Yeah, this is correct. No, this is correct. So it will be starting from I naught plus 1, so it will go to, sorry, it will go to x I naught minus x I naught minus 1. Next is fc to fx naught, x I naught. Next is f x I naught plus 2fc. Next will be, yeah, second one will be I naught to I naught plus 1. Next one will be I naught plus 2, 2, okay, this will be 2. This will be plus 2. I naught plus 2 to this, okay. So this is the thing. This is the thing. And now this can be written as, this can be written as, this is not that. Here is the thing. Here is the thing. Note that a equals to x naught less than x1 up to the point x I naught, x I naught minus 1 mm, x I naught less than equals to less than c. This is a partition of AC and C less than x I naught plus 1 all the way xn is a partition of CB. Then this is the corresponding T T. This is the corresponding TP1 dash F, where P1 dash is this partition, and this is the corresponding T P2F, where P2 is this partition. So therefore this will be this particular value Tp dash F. This will be less than is equals to this particular value will be less than is equals to the total variation of that A to C F plus Ta to Tc to B. Sorry, this will be T uh, C to B F. Okay, so now this will be T to T, and this is for every this is done. Okay, this is done. Now conversely, I have to prove the converse. Okay, therefore T A to B F is less than is equals to T A to C F plus T C to B F, because T A to B F is the supremum of T P dash F for all partitions. Okay, so therefore this is what happens. Now for the other part, what we will consider, let P1 is equals to x naught equals to A less than x1 up to point xn1. This is equals to C, and P2 which is equals to C is equals to x. I can take this is different. This is N, and another one is y naught less than y1 up to point yn, which is ym, which is equals to b to partition of A to C and C to B respectively. Okay, A to C and B to partitions of A to C and C to B respectively. Then P1 union P2 which is equals to x naught x1 all the way xn which is equals to y naught less than y1 all the way ym be a partition of m plus n nodes. Then P1F, which is restriction on A to C, this is equals to summation of mod of fxi minus 1 I equals to 1 to n, and P to F restriction from C to B is equals to summation of j equals to 1 to n 1 to m, basically 1 to m mod of xj minus mod of yj 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 minus 1. Okay, this is what we have. Now also t p1 p2 comma f, this is equals to summation of I, this is equals to summation of t p1 f restriction of a to f plus t p2 comma restriction of c to b. Okay, this is what we have. Now fixing and that implies this is less than equals to t a to b f, right? Now by fixing the partition p1 and taking supremum over taking supremum over we get t p1 comma f restriction of a to c plus t c to b if this is less than equals to t a to b f. Now again taking supremum of supremum over all partitions p1 of a to c p1 of a to c, we get t a to c f plus t c to b f, which is less than is equals to t a to b f. So if we give it 2 and if we give it 1, then by combining 1 and 2 we get t a to b f is equals to t a to c f plus t c to b f for all a less than c less than b. This completes the solution of the problem 4. Now we'll try to do another problem. So let's try to do another problem, problem 5. Problem 5. So what it says, let f from AB to R be an absolutely continuous function be a absolutely continuous function. Be absolutely continuous function. Let f from AB to R be an absolutely continuous function. Next, so that T A to B f is equals to A to B mod of f dash dm1 P A to B f is equals to integration A to B dm1 and in A to B f is equals to integration A to B f dash minus dm1. Here TAB we have know what is TAB. F dash is the derivative, okay, and the PAB is equals to supremum over all partition of the fact this plus this is the maximum of I equals to 1 to n, where x naught less than xn be a partition, be the partition P of A to B interval. This is the partition P of A, and for any real number R plus is equals to maximum of R comma 0, maximum of R comma 0, R minus is equals to minus of minimum of R comma 0. Okay, this is plus and minus, and NAB is actually in terms of supremum over all partition P of the interval AB, I equals to 1 to n f of xi. This is minus. This is what it is. Okay. So now we'll be doing this one. Okay. So here it is given that what is the condition given on f? F is absolutely continuous. Recall that when a function is called absolutely continuous, we call that a function f is called absolutely continuous on the closed interval ab if for any given epsilon greater than 0 there is delta greater than 0 such that for any finite collection of, let's give it different name, k, of disjoint intervals ab such that then summation mod of fxi I equals to 1 to k less than epsilon. So I think it has been proved that if a function is absolutely continuous, then it is a bounded variation. That's separate thing, but this is not to our target. Our target is to okay. If a function is absolutely continuous, then we have to prove this one. Okay, I will take a help of the theorem which is already been proved in the class, which is already in the lecture. So I'll take that help. Otherwise, this will be very big. Have to very big problem. Otherwise, first of all, the first one is there. There is a theorem. It is absolutely continuous. Okay. Okay. For an absolutely continuous function, we have to prove this one. So let me a little bit. Then it okay. Yeah. Okay. Here I'll take little help of the theorem and other part I'll prove. Okay. So it is theorem one can say. If a function is if function f is absolutely continuous, f is absolutely continuous on closed interval AB, then f is a bounded variation. F is of bounded variation on AB. Second theorem, if f is a function of bounded variation, if f from AB to R be a bounded variations, if f is a f from AB to R be a function of bounded variation, then the total variation, then f dash is integrable. That means it is differentiable almost everywhere. Why it is differentiable almost everywhere? Because if a function is a bounded variation, then it can be written as the difference of two monotone function. Okay, into in monotone increasing function. If a function is of bounded variation, then it can be written as the difference of two monotone increasing function. And a monotone increasing function is differentiable almost everywhere. So therefore, if a function is a bounded variation, that means it is integrable. F dash is it is differentiable almost everywhere, and let f dash be the corresponding derivative. Then it is also moreover it is satisfied that f dash is integrable, and the Lebesgue integral of f dash dm1, this is less than equals to TAB, that is the total variation. So now only we need to prove that only we need to prove that TABF is less than equals to DM1. So this will give the first part, right? This will give the first part. Now for any partition, no, this will give the first part. Now for any partition, x0 is equals to a less than x1 all the way less than x equals to b of AB, summation of I equals to 1 to n mod of fxi minus mod of fxi minus 1 mm, I have to prove that this one is less than or equals to this particular thing. Okay, General advantage option within solve that six. This way to okay. Yeah, we need to only prove that this one. Okay, yeah, that's correct. So then, okay, this can be written as summation of I equals to 1 to n integration f dash x I minus 1 xi dm1. Why this is? Because if a function is this is already there, this is already there, this one, this one is less than is equals to summation of I equals to 1 to n integration xi minus 1 xi mod of f dash dm1, which is equals to integration a to b dm1. So, but this is true for every partition. So, therefore, as this is true for every partition, as this is true for every partition P of the interval closed interval AB, then we get then that supremum over partition will also be less than equals to this. So that means TABF, that is supremum over all partition over P comma F, that summation of mod of xi comma xi minus 1 I equals to 1 to n. This is less than is equals to integration a to b mod of f dash dm1. So this will complete the proof. But why? Where is the only fact is that this is the fact. So note that only the point is that note that we use the fact f of xi minus 1 is equals to integration a to b, sorry, integration xi minus 1 to xi f dash dm1. This is what we have used. How one will get this? Suppose f is a function. Suppose it is given that it is known that if a function is a bounded variation, note that it is known that it is known that F being of bounded variation f dash if is differentiable almost everywhere, that is for sure, and f dash is integrable, and and take hmm, so and the other around will hold also, that fxi minus fxi minus 1 is equals to integration. This will hold, but okay, I think this is okay. We don't need to do anything because f is there is a theorem which I don't want to write. If f is absolutely what is called absolutely continuous, then it will be integrable, and the function integral, then the function f defined by f of x is equals to integration a to x f dash dm, sorry, not a to x, a x is differentiable almost everywhere. Almost everywhere, and f dash x is equals to f of x. Okay, so therefore, then f of xi minus f of x minus 1, that f dash xi minus xi minus 1, this is, yeah, mm, this is what it is. So f dash is equals to, this is f dash. Okay, no, sorry, this is what it is. This is what it is. Here f dash is integrable. Here f dash is integrable, then the function f defined by this is, and this is equals to this. Oh no. Then f equals to this one. This is correct. This is correct. So therefore this is equals to not this one. F is f being bounded variation, f dash is integrable. Okay. Acha, f dash is integrable. That is f equals to f almost everywhere. And this will give f equals to f almost everywhere. And this will give f of xi minus 1. This will give is equals to f of xi minus 1. This will give integration a to xi f dash dm1 minus integration a to xi minus 1 a dash dm1, which will give xi minus 1 to x f dm1. So this is what it is. Now for the next part. What next part says, we'll be using similarly. What other part says, that that PABF is equals to f dash plus dm1. This is what I have to prove. Okay. It is known that f of b minus f of a is equals to PABF minus NABF. Okay. And and f of b minus f of a is equals to integration a to b f dash dm1, okay, which is equals to integration a to b f dash plus dm1 minus integration a to b f dash minus dm1. So that is PABF minus NABF is equals to integration a to b f dash plus dm1 minus integration over a to b f dash minus dm1. This is the first one given in, and then the next one is that also for absolutely continuous function, these are for all absolutely continuous function. These are all true absolutely continuous function. Okay, these are all true for absolutely continuous function. Okay, so below thing also, the whatever I will write, these are for absolutely all for absolutely continuous function. Also, the TABA that which we have proved few minutes ago, that is A to B mod of F dash DM1, which we proved now, which we which we just now. Okay, A to B. This is not mod. This is just. This is mod. This is not box. Okay, this is, and this is equals to integration A to B F dash plus dm1 plus integration f dash minus dm1. Also, TABF is equals to PABF plus, sorry, not PAB, this will be NABF, okay? And now give it name 1, give it name 2. Now by then clearly, then from 1 and 2 we get PABF is equals to integration A to B F dash plus dm1 and NABF is equals to integration A to B F dash minus dm. I think this is what we are asked to prove, right? I think NAB is equals to F dash minus and PAB is equals to F dash plus. Yeah, this completes the proof. So I'll not do any more problem. Okay, I'm not right. So here what we have used basically the fact that f is absolutely continuous. So one fact is that, so what is the important fact is that if f is absolutely continuous, so here is the one for the if if f is absolutely continuous, you can write here if f is absolutely continuous, f dash exists almost everywhere and integrable. Not only that, f of x is equals to f of a2x f dash, not a2x dm1. So this is what very important thing, and this is what crucially using. So let me check this is I'm saying correctly. Hmm. Very important. This theorem is very important theorem. So this is what we are using both the places. I mean all places we are using this fact, and we are trying to prove that. Okay. Okay. So this is what. So what we have actually today as a problem discussed. We First we discussed. Okay. First we discussed the monotone function. For the monotone functions, both the left and right limit at any point exist, but they may not be equal. But if it is equal, I mean, the point is that if we take a point for a monotone increasing function or monotone decreasing function, then at that point both the limit on left hand side and both the limit on the right hand side exist. And if they are equal, then we say the function is continuous at that point, and if it is not equal, then we say the function is discontinuous at that point. So therefore, for a monotone function, the discontinuity can only be jump discontinuity. Okay, they both left and right integral must exist. They may not be equal, but they must exist. Okay, the jump discontinuity. Next, we have proved that the number of discontinuity of a monotone increasing function can be only countable, not uncountable. Okay. Then we have given a function, and for that we have computed the d plus f, d sub plus f, d super minus f, and d sub minus f. And next we give a function which is a bounded variation. Okay, this is we have given a function which is a bounded variation. And uh, next we prove this bounded variation, total variation. This is called total variation of a function of bounded variation f on the interval ab. So this total variation on the interval ab is equals to total variation on the interval a to c and c to b, where c is in between point a to b, that we have proved. And next we have uh, obtained another problem, the total variation for a absolutely continuous function. The total variation is actually the Lebesgue integration of the function mod of f dash, where f dash is the derivative of that function. Okay, so this is all. So in the next day we will be continuing from the after this point. Okay, so the next tutorial will be on the next Saturday, 6 to 8 p.m. Thank you.